So first of all, I have to thank all the organizers for inviting me. I think I'm the outlier, which is a good time slot to give to an outlier, because at this time of the day, I'll kill everybody. That's, I think, and that's my weapon of choice. I'll write on this whiteboard behind me. So I'll show this strange theory, the power functional theory, and we have memory. It's very different from the generalized Langevin equation. We haven't got projection operators, etc. It's not Moritz-Zwanzig. So I feel guilty a bit about being exposed to so much material. And the primary example, the one that I've chosen and want to talk primarily about, is one that is based on molecular dynamics, and it's carried out by Daniel de las Heras and his PhD student Joe Renner. And I'll speak about this, and it connects to Felix Höfling's talks, where we look at friction and, or maybe more specifically, viscosity in an MD setting. And I want to explain why we look in this, I think, strange way for you, want to explain this concept, the power functional concept, briefly at the blackboard before. There's other cases. These are all Brownian dynamics studies that Lukas Treffenstedt has done. This is the Van Hove function in a Brownian dynamics hard sphere, where we find memory. Flo Samula has developed a Brownian dynamics, adaptive Brownian dynamics algorithm that I at least want to mention for people who are interested in methodology. And Sophia Hermann has derived some rules, again, for the Brownian dynamics. So I'll stop this. You have to pin me in order to see, to make me large enough, right? Which is maybe not what you want, but otherwise you can't read. So I'll spend 10 minutes or whatever. It won't be 10 minutes, right? A speaker at that time of the day, when they say 10 minutes, I wouldn't trust them. But that's my plan. To show where we start and where we try and get with this, right? And then I switch to the graphs, and those who aren't dead by the by the pen, I will try and kill with the graphs. So where are we coming from? You've seen this before. Leave some space, and I put a density operator and average this, and the RIs are of course all the coordinates. And for a moment, let's do Brownian dynamics. I'll show you the MD. I think most people are more interested in molecular dynamics. I'll show you on the PowerPoint the molecular dynamics version. That's the same, actually. It's one body density. And if I only have space point, that R is the same as that R, then there's the one body density. And of course, I'm heading towards density functional theory that many people will know. Now, in that case, in equilibrium, this will be an equilibrium average over Gibbs-Boltzmann distribution, etc. Maybe grand canonical, whatever. But let's say the average is now over a non-equilibrium distribution function, okay? And then this, the one body density starts also to be dependent on time. And I have to prescribe some microscopic dynamics, how these guys move in time, right? And there's two choices. Later, I'll show you the Liouville equation. So this is just MD. They just move, sort of the distribution function just evolves according to the Liouville equation. Or for the stuff that I write down here, let's suppose this is now Brownian dynamics. So there's a Langevin equation on the many-body level for these things, not generalized, just instantaneous in time, or a Smoluchowski equation that moves the distribution forward. I want to do time-dependent non-equilibrium phenomena. And the big thing of the PFT, of the power functional theory, is that this quantity isn't enough to understand the motion in the system. And that's why the current is also important, J of R and T. And it's a similar object, but there's the velocity at the same time, right? And this is again averaged over the non-equilibrium distribution. Okay, same thing. One can worry about a bit what the velocity is, but there's a proper solution in the Smoluchowski picture. That's a well-defined thing. And also in Brownian dynamics, in an Euler algorithm, one can jump forward and jump backward. It's a center derivative that does the right thing. And this object is on a one-body level of correlation functions. It's really the central correct thing to characterize the motion of, and of course they're connected by a continuity equation. I mean, I don't have to write it down. And integrating, knowing the current, I can integrate up and know the density. Now, as a preview for the MD case, there is a third equation, which is an acceleration density, because this thing is, the MD dynamics is a time derivative higher, so I have to go a time derivative higher. Okay, these are the variables. Why am I stressing this? And for this audience, I haven't said anything interesting. It's a trivial point of view. There is something in the PFT that gives these quantities a special, meaning as variational fields, and this is unusual. And I want to make that point. That's the only point that I want to make at the whiteboard. So how do these things move in time? And there's a force balance relationship. That's a friction constant. The in BD, they move against the background. It's an input quantity, and I leave away the arguments. And then this thing, or maybe I do it with a velocity. So I take the current, divide by density, all with the same arguments. It's a velocity field, it's a V. And there's a drift term, grad of log of rho. Okay, that's just a thermal diffusion. And then there is an F, an internal force field, which is also, of course, space and time resolved. Okay. And then there is, in general, also an external, I put the arguments, that drives the system out of equilibrium. So in the case that I'll show later, that's a shear field, for instance, that drives now the one-body dynamics. So the whole approach is done on the one-body level. And of course, this thing is again an error, can be written down as a correlator. But I just would put the force on particle I in the average. Okay, and then we have to actually simulate to get these quantities, and that's how we get reference data. So the PFT, if I write down it says there's a functional RT rho J, and this is the variational principle. It's 0 at the true dynamics with the proper minimum. And you could say, well, what does it mean? Is this important or not? And the important thing from this follows a certain property of this force field. Because again, at the moment, if this is again given as an average, I have to solve this Minkowski equation, which is of course impossible, or to be done on a computer. So what this equation leads to is that the if internal is generated RT, this is the functional now of the density and of the current, and it's generated from an excess. That's now a detail. This is also functional of these two things. That's J, sorry for the writing, and the derivative is the same as that one above, right? This is the interest, the PT excess super adiabatic on top of free energy is the interesting part. It's a sum. There's boring bits that I don't write down, and that's the interesting part in the dynamics. Now, this all looks very formal, but it's a describes the way of thinking about these problems, because something important has happened now. This internal force field doesn't depend anymore on the external forces. If you have calculated this as an average, the external forces were there to get the average distribution. But this is now free of the external forces. It just depends on the motion of the system. And I call this a kinematic functional. It's just a word, as opposed to a density functional, which would only depend on rho. This is a kinematic functional. It also depends on the flow. So, are there any questions at this point? No questions at this point. I take this as a good sign. So I show you the MD version in the PowerPoint, and then sort of the equations. They're a bit more complex, and then I show you the applications of this and try and convince you that this actually has practical consequences. If I can move my transparency. So this is already on the whiteboard here. We've got a typeset version, density. These are all time-dependent non-equilibrium quantities. That's the one that I haven't written down on the blackboard, but the minus is U is the interparticle interaction potential, Lennard-Jones or whatever these guys are. And this is normalized at little f. Maybe I've put it wrong on the, no, I've done it right on the blackboard. So, and there's an equilibrium part. Sort of the adiabatic part is just that in equilibrium, and there's a non-equilibrium part, which is on top of that. So the full interactions come from a free energy, from an intrinsic free energy functional, which is just the density functional, and they also come from a super adiabatic bit that is a kinematic functional. Okay, that's the general framework. And again, the adiabatic is it's the same correlator, but now evaluated for an equilibrium distribution, which is chosen such that the density field is the same. Right. So in MD, that's the case that I didn't want to show. The concept is the same. The expressions are more complex. Why are they more complex? Of course, there's now also transport effects. There's a kinematic, stress tensor that describes inertia. The variational principle looks similar to the BD that I've shown on the blackboard, but it's now a time derivative higher. So that's an acceleration density. J dot is really the time derivative of the current. And this is minimal with respect to this acceleration density at the real dynamics. And then one has to integrate twice in time to get from the J dot to the J and from the J to the rho. This is how this works. And the force density balance has, okay, this is also with a magnetic field written down. So forget about these terms. There's an external potential, time dependent. One can factorize an ideal term, which is there. This is just a factorized version. And there's an excess on top of this contribution, sort of the real one minus for the ideal gas, minus this factorized one. So this whole bit has the interactions in it. And again, it's free of the external field. That's very important. The external forces are not there. This whole thing is this kinematic functional. And it describes the internal interactions in this, on this level. So that was sort of sorry for the, rushing through this. This was sort of a glance of the general framework. And maybe if I go back, the thing is that this functional depends non-locally on time. Also, although this derivative is taken at a time t, the input fields of these are non-local in space. I mean, like in DFT, this is has all the spatial correlations in it. But differently from density functional theory, this also has a time derivative in it. Okay, and the dependence on this is a history type of dependence. So there is the functional eats all these fields up to time t and produces a value. And that means that this thing, which I've been stressing, that it's a kinematic functional, depends on the flow, also depends on this, on the past of the system. And we have a bunch of studies where we tested this. Is this actually, can one see this in real data? It's brute force simulation work and analyzing the data and trying to understand what's going on. And I want to focus on this acceleration viscosity case that we've identified in MD. This is unpublished work, and briefly mention just this case, Sophie Hermann's Noether's sum rules, just to give you a flavor. Because this super adiabatic contribution is now, it doesn't depend on external, it just depends on the, say, Lennard-Jones interactions. And one can apply symmetry operations and get identities from the underlying symmetries of the Hamiltonian, of the intrinsic part of the Hamiltonian. And they look, this is an exact identity. It's a representative example in the paper. We have, lots of such equations, and they have a time integral in them. I mean, they will again look, I guess, strange to many, knowledgeable people in the audience. They connect these one-body quantities. Arguments are left away. Prime is is T prime and R prime. That's what the prime indicates. And these things are higher derivatives. So they are like memory. Okay, are they memory functions? We can get these from second derivative. That's what the 2 is from this super adiabatic power functional that I've written on the whiteboard. And this is a strange relationship because we don't know what it means. We don't know what these kernels are, but they constrain in a way, you know, the functional itself and give additional structure, which just comes out of the fact that we start from a variational principle. That was a side remark. I want to focus on this point and primarily talk about the applying this now with real MD data. That's what Dani de las Heras and Joe Renner have done, and show you that. So the assumption is, because we have this functional, that's the interesting bit of the functional, and we make an assumption of how the functional looks. So just briefly, there's a memory kernel. This is taken, this is, you know, very, very poor memory kernel. I learned that it's, you know, it's just exponential. Even in this form, it's dimensionless. So the amplitude is taken out as a constant. And then the functional couples the rod of the acceleration. A is, you know, is j dot divided by density, and v is the velocity field. So it couples rho is density at this space-time point, rho prime is at the other space-time point. Yes, it's local or semi-local in time. So there's nothing more happening than a you know, this what is sometimes called semi-local. So just we haven't got a real convolution kernel in space, but have got this simple convolution kernel in time. And there's now one can build just from counting the powers in this. So it has to depend on acceleration by construction. And then this can couple to velocity and it can couple to acceleration. And similar for the divergence. So the word is a bit funny because everything is inhomogeneous, right? And in the examples that I showed, everything is inhomogeneous. And the bulk viscosity is, you know, extensional or volume viscosity, but on a microscopically resolved level. So in the sense that it couples to compressional flow and compressional acceleration. And that is just from, you know, blue sky thinking, what should the functional low orders in these fields, quadratic structure with a simple memory kernel? This is just an assumption. And then the derivative, okay, I don't want to kill, maybe I want to kill you with these formulae, but the derivative generates the viscous response in the system. Okay, here's the real data. Does this stuff work or not? And we've made a situation, custom flown a situation that I want to explain to you what our real system is. So it's a 3D repulsive Lennard-Jones system, and it undergoes this non-equilibrium time evolution. Something is switched off, something is switched on, kept constant and switched off again and relaxed. And this time is long enough, tau is the intrinsic time, such that it's, you know, it's practically in a steady state there. And what is switched on, that's the current, it's the global current in the system in one direction. So just in one direction, it's inhomogeneous, and in the other directions, it's you know, translationally invariant. So that's the x direction. And this graph is the density profile. So it's just a sine wave, or minus cosine rather, right? So the system has a density wave, and then there's flow through this density wave, okay? That's the external field that generates this, and we have what we call a custom flow method to prescribe the density field because we want, you know, something simple here and have simple time evolution, and then the custom flow algorithm generates the necessary external force that generates this. And it looks a bit funny, but let's disregard this because the external forces, they split off. We don't have to worry about them. Okay, that's the density profile. The current is constant by construction. That's again what we want, because we want to switch off a lot of the time dependence, not have it, right? And just focus, reduce, if you like, the time dependence in this non-equilibrium situation. So the color code is, right, the red one, we go up in current, and that's a velocity profile. Okay, so this is still small, it grows larger and it's smaller again, and then it's zero. At this switch off time, there's no flow anymore. The system is on the one body level at rest. And then, of course, multiplying these, right, gives this constant, because the velocity times the density locally resolved is the current, and the current is per construction constant. So this is why this has a slightly funny shape. It's just 1 over cosine, right? Now, what we do measure is two fields. That's the acceleration, okay? Maybe these three are rather, these are the kinematic fields. That's the acceleration. So initially, the acceleration is positive, right? We go up this wing, acceleration is positive, then there's no acceleration, and then we go down again. So the acceleration flip sign, okay? And the acceleration in space, again, is of course inhomogeneous because we're flowing through this, you know, through this density landscape. Now, in this graph, you also see already, although I have a few more graphs, but in this, you see already that something strange is happening. Because that's now the internal force, that's the viscous force, and it's the raw data from the MD. There was no theory so far. This is just raw MD data. There's no thermostat. We do low driving. The heating up isn't very strong, okay? And then at this point, this is the response. We're testing bulk viscosity, also done the shear, but you know, it's slightly more complex to explain. That's why I explained the bulk or volume viscosity. And you see that this curve is more or less that one, but the second derivative, as you would expect. Sorry, I meant the wrong graph. This is more or less that one, the second derivative, which you would expect the Stokes, you know, just the Laplace of V is the viscosity. Okay, and this is when going up and when going down. And then the system is at rest, but at rest we still have a signal, and this signal is the other way around. This is now the second derivative of this guy, right? Going down, the acceleration is flipped. So there in the viscosity, there's an acceleration term. And of course, this is a high frequency in other language because this all you know, time domain. It's a real, it's a high frequency effect. So the same thing, I save you from the shear, we have done it in shear. And this is the results that summarizes, if you like, the agreement with the theory, the many equations that I've shown before. So the C is a constant, it's sort of a scalar, sorry, not constant, it's a scalar measure of the overall agreement. We get the profiles. I don't show you the data, but that's a measure of the overall agreement because they're just second derivatives. They're well controlled if I go back. They're well reproduced by these derivative expressions. We haven't got any doubts with these, but we want to look at the memory. And then these two expressions, the velocity alone, sort of Laplace velocity plus the density dependence, of course, creates a green signal. And the Laplace acceleration creates this little blue signal. Oops. So there's an overshoot in this viscous response, and then there's an undershoot when switching off again. And the same thing for Brownian dynamics doesn't occur. There's no overshoot and no undershoot. And this is consistent with what I've written at the whiteboard, that in MD there's an additional dependence on the acceleration again. And the important thing, if I go briefly back to this, is that the kernel is very simple that we need to describe this. So this has just a memory time in it and a total amplitude, which is taken out there. And we're not putting, or don't have to put, if you like, or don't see any complexity really in the memory kernel. And the reason for that is that, if I go back again, sorry for the jumping around. The reason is that this kinematic functional, you know, has the freedom of depending on all these fields, but on nothing else. It has sort of the complexity is already in this dependence. And then it turns out the memory kernels are very simple. So how much time have I got? Is it 5 minutes or so, Thomas?
Yes, 5 minutes.
Okay. And or am I killing my discussion? Because maybe I go briefly, then people can ask questions. Maybe just briefly, this shear case, in the shear case, it's the splitting, although I haven't explained the setup, but just if I focus on this point, this is the velocity, viscosity, and that's the pure acceleration viscosity. And the real signal is sort of the wiggly line, of course, is the full data. And the purple line is the theory. So it really mixes both of these contributions. And we are not, please do tell me if somebody has seen an acceleration viscosity before. So maybe 1 minute. This is now BD, and maybe some people aren't as interested in that as in. That's why I focused on the MD case. But we looked at the, it's an old problem. What is the Van Hove dynamics? Just microscopic two-body dynamics of a diffusing self-particle now in a quiescent liquid. There's no drive. It's just this guy diffuses. And via the dynamic test particle limit, one can describe it on the one-body level. So this guy has a self-particle has a density field, and all the distinct particles also have a density field, and the dynamic test particle then moves, if you like, this Van Hove dynamics on the level of a one-body problem. And it's a non-equilibrium. Strangely enough, it's a non-equilibrium problem on the one-body level because the self-particle is fixed at the origin initially. And okay, that's an overkill plot, of course, but we find the same type of super adiabatic forces that we find in other systems. Maybe if I go back, when the system is driven, one can identify super adiabatic forces that just depend on the way the system moves, but not on the type of drive. That's a very important type of universality. And these, I haven't got time to talk through this, but the theory, which are the lines against the simulation data, is taken from genuine non-equilibrium situations, such as active Brownian particles, laning systems, etc. So maybe I should just shut up and thank you very much again to the organizers for giving me the opportunity, and I'm looking forward to your questions if there are any at this time of day. Thank you very much.